All right. Good morning, everybody. Welcome back. So, for today, we will have the first 20, 30 minutes lecture, and then after that, we will move on to the in class assignment number 6. So, we are still in the final stretch of chapter number 6. So, let's pick up where we left on Tuesday. Okay. So one of the last things we talked about on Tuesday was the concept of allotropes. Okay, remember that allotropes are compounds with the same composition but connected in different ways. And because they are connected in different ways, the physical and chemical properties will change. And just in here is a better definition of allotropes. You may have an allotrope when a compound is formed only by one kind of element. Okay, so graphite and diamond, they are formed only by carbon, therefore the nomenclature allotropes. When we move on to the organic chemistry, we also can have carbon connected in different ways, but the compounds are formed usually by carbon and hydrogen. Okay, so not just one kind of element. And that's why we don't call them allotropes and we call them isomers. And that's the difference in the nomenclature.
Thank you.
Uh-huh. Okay, and remember that the enthalpy of formation for the most stable allotrope is always 0. If a compound or an element does not form allotropes, then you have to know that the enthalpy of formation is going to be 0. Okay, today what I would like to show you, and that's the only thing I will show today, is the Hess's law. So Hess's law is another way to determine the enthalpy of reactions. Sometimes reactions are very complex and it's hard to measure the enthalpy of just that reaction, or for some reason it's hard to measure the enthalpy of formation of a given compound. And then we are going to use the Hess's law. Hess's law will take advantage that energy is a state function, which means it only matters where it starts and where it ends. What the reaction does in the middle to get from starting point to end point, it does not matter. So we can do an analogy here. If we start from the base of this mountain here and we want to achieve to go all the way to the top. You can start from this point and go in a straight line and get to the top, or you can start here, go in diagonal all the way here, go here, here, or there. You also going to achieve the top of the mountain. So if we measure the height that we needed to go from bottom to top, it doesn't matter if we measured from here to here, or from here, 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 or here, the height is the same. And that's the same idea for chemical reactions. We may take just one direct way to the product or go through intermediate steps to get to the end. It does not matter. Therefore, the overall reaction enthalpy is the sum of the reaction enthalpies of the steps in which the reaction can be divided. Okay? For the Hess's law, we are going to treat the chemical reactions as mathematical equations. So we can manipulate them in any way we manipulate mathematical equations. Okay, so let's see an example here and see how we can use the Hess's law to get the enthalpy of an unknown reaction. So imagine here that we have a problem and that the goal here is to determine the delta H for the enthalpy of this given reaction shown here. So we have water in the solid state going directly to the gas state, and we don't know the delta H for this specific transformation. However, we know the delta H from water going from solid to liquid, and that's 6 kilojoules per mole. And we also know the delta H for water going from liquid to gas, and that's 45.1 kilojoules per mole. So the first thing I want to do here is to draw the energy diagram for each of those transformations, okay? So let's put in a single energy diagram the two steps. So let me switch screens. Okay, so let's draw the energy diagram for these two reactions, and I want to put in the same energy diagram both steps. So let's do a big one here. Energy is going to be our y-axis. So let's start with the reaction number one. So we are going from water in the solid state all the way to the liquid state right here. Okay. The transformation is endothermic because the delta H is positive. Therefore, the energy of the products is higher than the energy of the reagents. So we go from down all the way up here. The delta H is the difference between these 2 points over here. And we know that for this reaction is going to be 6 kilojoules. Now in the same diagram, I want to draw the energy diagram for the second step. So let's put that in red, the second step. See that the second step starts where the first step ends. So we are going to start from water in the liquid state and go all the way up to water in the gas state. Again, delta H is positive, therefore the transformation is endothermic, and the arrow is going to indicate the direction of the transformation from liquid all the way to gas. The delta H is the energy difference between reagents and products, and for this case is 45.1 kilojoules. Okay, so all the way up here. So for some reason, it takes more energy to move water from the liquid state to the gas state than compared with solid state to the liquid state. Okay, so now I know the first and second steps in the energy diagram. And let's draw next to this energy diagram what we are looking for. What is our problem? In our problem, we want to know, oops, the delta H if we start from water in the solid state and go directly to water in the gas state. Okay, So we need to know what's the delta H for this whole step here. And that's our goal. Looking at both energy diagrams and comparing them, can you see that this whole delta H that we want to know is basically the sum of the first step and the second step? So this whole thing here is basically the first step plus the second step.
She will come down here from California.
And that's what the Hess's law says. It doesn't matter if we go directly from solid to gas or in individual steps, the delta H has to be the same. Therefore, the delta H for the direct transformation between solid and gas is going to be the delta H for the step number one. I'm going to represent as delta H1 plus the delta H for the step number two. And that's going to yield 6 plus 45.1. Therefore, the delta H for the direct transformation between solid and gas is going to be equals to 51.1 kilojoules. Okay, so that's how you can use small reactions to get the delta H for larger reactions or steps that you don't know. So now let me show you how to use the equations and manipulate them as mathematical equations to achieve the delta H of more complex reactions. So the first trick here is to look at the problem. In the problem, we have water in the solid state as one of the reagents and water in the gas state as the only product. Now look at the reactions that are given and let's try to manipulate the reactions in order to get what we need. So let's look at the first reaction. The first reaction has in common with the problem reaction water in the solid state, and it is already in the reagent side. So let's keep the first reaction as it is. So let's just rewrite it. And the delta H for this reaction is 6 kilojoules. Now let's look at the second reaction and see what the second reaction has in common with the problem reaction. Both have water in the gas state in the product side already, so we will keep the second reaction as it is. Water liquid going to water gas. And the delta H for this step is 45.1 kilojoules here per mole and per mole. Now the trick here is to add up everything that you have, and you can treat the chemical reactions as mathematical equations. In a mathematical equation, if you have water on the right side and water on the left side in the same physical state, that can be canceled. What's left here is water in the solid state, and the only product that's left is water in the gas state. What about the delta H? If I'm adding up, I'm going to add up the delta H as well, and this is going to give 51.1 kilojoules per mole. So we got the same number as we did using the energy diagram. Okay? And that's how the Hess's law work. In the event that you need to flip equations, the delta H has to flip signs. If you multiply a chemical reaction by a given number, the delta H has to be multiplied as well. And this is how you're going to use small and simple reactions to get the delta H for larger and more complex reactions.
Mute yourself.
Okay, so now let's try to solve a more complex problem here. So here is the proposed exercise. So the question here is that we are looking for the delta H for the third reaction over here. Chlorine plus ozone giving chlorine monoxide plus oxygen. The informations that we have is that we know the delta H for the reaction or the equation number one, and we also know the delta H for reaction number two. So how can we manipulate these two equations to get to the delta H for the third reaction? So let's first look at what we have in the problem and look at the first equation and see what they have in common. Our problem equation has chlorine gas on the reagent side and chlorine monoxide in the product side. Our equation number one also has chlorine and also has chlorine monoxide. So that's a good sign. However, chlorine is on the product side and chlorine monoxide is on the reagent side. So see that the first reaction has two things in common as our problem reaction. However, it is flipped. So we are going to have to to fix that. So the way to fix that is to invert the first reaction to achieve the same common characteristics as the problem reaction. So that's going to be our first step. So we are going to invert reaction number one. Inverting reaction number one means that now the products are going to be reagents and reagents are going to be products. So it's going to be chlorine gas plus 2O2 gas producing ClO gas plus ozone gas. Okay? Always pay attention to the physical states when you are doing that. So now that we inverted the reaction, we also have to invert the sign of delta H. So the delta H was minus 29.9 is going to be plus 29.9. So now let's look at our second reaction. And again, let's see what they have in common, what it has in common with the problem reaction. So we have ozone in the problem reaction and ozone in the second reaction, O2 and O2 in the second reaction as well. Now, the second reaction has ozone as reagent, the same thing for the problem reaction, and oxygen as a product, and the same thing for the problem reaction. Therefore, we don't do anything with the second reaction. We just rewrite as it is. So we are going to have here 2 moles of ozone gas producing 3 moles of oxygen gas. We didn't do anything with this reaction, therefore the delta H is still unchanged. Okay, 24.18 kilojoules. Now, what we are going to do is to simply add up the two reactions and treat them as mathematical equations. Chlorine plus 0 still remains chlorine gas plus, now pay attention, we have two ozone molecules on the reagent side and just one on the product side. Therefore, we can cancel this ozone with the two over here, and what's left is just 1 mole of ozone. So we are going to treat exactly as mathematical equations. That's all for the reagent side. Now let's take a look at the two molecules of oxygen here for the first one. And now we have 3 on the other side for the second one. So we can cancel 2 with 2 over here. And what's left is just 1 oxygen. Chlorine monoxide doesn't have anything in common. Therefore, we just repeat it. So that means the sum of the inverted reaction 1 plus reaction 2 gave exactly what we needed for our problem reaction. So always make sure the stoichiometric coefficients are matching as well the physical states. Now, what about delta H? Well, we just summed the two reactions. We are going to do the same thing for the delta H. 29.9 is for the first one, plus 24.18 for the second one. Therefore, the delta H that we were looking for is going to be equals to plus 54.08 kilojoules. joules per mole. And that's how you use the Hess's law to get the delta H of more complex reactions. Always treat chemical reactions as mathematical equations. So inversion of a chemical reaction will change the delta H. If you need to multiply the reaction by a factor, also multiply the delta H. And then at the end, add up all the small steps to get to the big reaction. Okay?
I have a question.
Yes.
Can you only cancel between the two lines across products and reactants?
Yes. If they are in the same kind of column, then you will add up them.
Thank you.
Mhm. So imagine that you have an equal sign here at the arrow. So if it was a mathematical equation, you just can cancel things that are on the opposite sides of the equal sign. Okay, so let's take a 3-minute break and let's come back at 11:31 to start the in-class assignment. All right, so let's start the in-class number 6. So starting with questions 1 and 2, let me know when you are ready to move on.